So this is single-ended LNA. So now we are going to go for differential LNA. So one single-ended LNA has very good performance, but it has one important drawback. It is sensitivity to ground inductance. So parasitic inductance, we are using many inductance here. So that inductance may cause issues in the single-ended LNA. So we are going to ensure that this inductive effect is going to be completely cancelled out. So how we are going to do that? Instead of taking the output from one drain and one ground, we are going to take the output across the two drain of transistors. Okay, so that will reduce the differential, that will make your differential LNA even more effective. So, and what happens when you are going to fabricate differential LNA, very, very small value of inductance like 1.4 nanohenry has to be fabricated. So that is going to be a very difficult task in your differential LNA. So maybe I'll show the diagram. Here you can see the diagram here. This is the differential LNA. As you can see, the output is taken across the drain of two transistors. And you see in the input side, you have an RLC circuit for biasing. Outputs, here you have LS for bias circuit. And here in the one more input side, you have RLC circuit. And these will ensure that the input signal alone is effectively passed. So other frequencies are going to be completely blocked out. And very importantly, I take output across the drain of two transistors. Okay, so that in single-ended LNA, I was taking output from one transistor and my negative of output was going to be grounded. Okay, so that is the case. And in the differential structure, this one is very symmetric. If you draw a line exactly here, and if you cut the circuit, it will be exactly same. Because of the symmetry in structure, you can fabrication is very easy, analysis is very easy, and since you take outputs across the drain of two transistors, whatever negative effect you have in the circuit, that will get cancelled out, because V out is going to be V1 minus V2. V1 is output of this transistor 1, and V2 is output of this transistor 2. So V out equal to V1 minus V2. So any parasitic series resistance or anything in series will become irrelevant because of cancellation. Okay, since I take difference of output, the cancellation of things happen, and you can say that the input impedance is controlled only by LS, and it is unaffected by the parasitics, and LS is somewhere here. So this at the input frequency, the CBLG will resonate, so it will become a short circuit. So the input side impedance is dominated only by LS on both sides. That is what is shown here. And another important feature of differential configuration, it will reject the common mode disturbances. So we have in differential amplifiers, we have studied CMRR, common mode rejection ratio. Same thing here, differential LNA. So all the common mode signals are rejected here, means that they cancel out here effectively. So when you are going for mixed signal applications where supply and substrate may be noisy, in that case, it is very, very important to reject the noise signal and only consider the input signal. So in that way, differential LNA is going to be very, very helpful. And we are going to operate this at high frequency. So we are going to see how it is effectively rejecting the common mode signal at high frequency. That is possible by layout. And you know the structure is symmetrical, so layout is going to be very, very easy for this differential LNA. And the total power consumption also you can find is going to be 2 times of the 1/2 of the circuit. And noise figure is going to be very much higher, like very much higher than the single